Welcome back to 10-Minute Science. Last time, backpropagation gave every weight its derivative in one backward sweep. Watch the wave run right to left. Today, why making the network deeper breaks that sweep, and the first fixes that made deep networks trainable. Our cat network had just 2 layers. Modern networks stack far more. Watch the layer counter climb. The networks behind ChatGPT run about 100 deep. Some image networks pass 150. More layers, richer features, so deeper should mean better. But for years, that is not what happened. Look at the 2 curves, the loss falling as training runs. The shallow network learns. The deep one barely moves. Deeper meant worse, and it was not a bug in anyone's code. Keep your eye on that flat, deep curve. The problem sits inside the math we built last episode.
Here is why.
Pick one weight in the first layer, the gold line. Its path to the loss runs through every layer, and from last episode, each arrow on that path has its own local derivative. Derivatives along a chain multiply. Watch them fly together into the formula. 1 factor per layer. 10 layers deep means 10 numbers multiplied. That product is the whole story, because the gradient is the step. Every weight moves by one rule. The new weight is the old weight, minus a small learning rate times its gradient. Watch the top track. A tiny gradient barely nudges the weight toward its best value. The bottom track. A giant gradient hurls it far past. Too small and learning stalls. Too big, and it blows up. Now suppose each factor is around 0.8, just a little below 1. Watch the green signal travel back. Every layer multiplies it by 0.8, and it shrinks. After 10 layers, only 1/10 survives. After 30, 1,000th. After 100, watch the counter. Essentially 0. The gradient is the learning signal. It tells each weight how far to step. Look at the bars under each layer. The last layers get a healthy gradient, so they learn. But the front bars get almost nothing. Those layers barely move. The front of the network is frozen. This is the vanishing gradient problem. Now flip it. Make each factor 1.5, a little above 1. 10 layers in, the signal is nearly 60 times too big. 30 layers, watch it, almost 200,000. The weights take giant steps. The numbers blow past what the computer can store, and training collapses. Exploding gradients, the same product, run the other way. So a deep network has to balance. Watch the band around 1. Keep the factors inside it and the signal holds. Drop below and it dies out. Rise above and it blows up. To train 100 layers, the product has to stay close to 1 at every single layer. So let's look at what those factors actually are. So what is one of these factors exactly? Zoom into a single layer. It takes the value coming in, multiplies by its weight, adds a bias, and passes that through the activation. Ask how its output changes when the input moves, and calculus gives one clean answer. The activation's own slope times the weight. That slope is the gate. Every factor is the gate times the weight. Now the 2 pieces behave very differently. The gate is the activation slope, and every activation caps it. For the sigmoid, it never passes a quarter. For tan, it tops out at 1. For ReLU, it is exactly 0 or 1. So the gate can only hold the signal back. The weight is ours to choose, any size at all. To keep the product near 1, we work on both. Before ReLU, neural networks ran on the sigmoid, the smooth S-curve from episode 3, squashing any input into a value between 0 and 1. It looks ideal, bounded, with a derivative at every point, exactly what backprop needs. Now draw its derivative, the orange curve underneath. At its very best, right in the middle, it reaches 1/4. Out on the flat ends, where the S saturates, it is nearly 0. And remember what this number is. The activation's half of every layer's factor in our long product. So even in the best case, every sigmoid gate multiplies its share of the signal by 1/4 at most. Watch the product fall. 10 layers turn 1 into roughly a millionth. Deep sigmoid networks refuse to learn, and it took the field years to trace the cause to this little quarter. This is the other reason ReLU took over. Episode 3 gave us the bend. Now watch what it does to the signal. On the open side, the ramp has derivative exactly 1, and multiplying by 1 changes nothing. Watch the pulse cross each open gate untouched, layer after layer. The flat side is still 0, so a closed gate passes nothing back, but every open one preserves the signal perfectly. That fixes the activation half of every factor. The other half is the weights, and before training ever starts, every weight needs a starting value. That choice matters more than it looks. The obvious first idea: start them all the same, watch every connection snap to the same value, 0.5. Watch what identical weights do. These two neurons take the same inputs times the same weight, so their formulas are the same, symbol for symbol. Same formula, same output. And because they compute the same value, the loss sends them the same gradient, the same step. After the update, they are still equal. They're clones, and nothing here can tell them apart. So break the tie before training starts. Give each weight its own small random value. Now the two formulas differ, different weights, so different outputs. Different outputs get different gradients, so the neurons pull apart, and each is free to learn its own feature. Random gives every neuron a different start, but the size of those random numbers goes straight back into our product. Now, watch the weight size. Too large and the factors sit above 1, the signal explodes. Too small, and it vanishes again. We need the size that keeps the signal steady. Back to the size. A neuron adds up n terms, weight times input, n of them. Here's the fact about adding random numbers. Their variances add. The variance of the sum is n times the variance of one weight. So as n grows, the spread of the sum grows with it. Watch the bar climb. To keep the output the same size as the input, that spread has to stay fixed. So set the variance of each weight to 1 over n. Watch the bar drop back to the input line. A bigger layer just means smaller weights, and the signal keeps its size, layer after layer. One question is left. Which n? The forward signal comes in through the inputs, so it wants 1 over n in. The backward gradient comes in through the outputs, so it wants 1 over n out. Xavier initialization splits the difference. Set the variance to 2 over n in plus n out. One rule, and both directions stay close to steady. It even ignores the bend between layers, and still works remarkably well. Now put it together. An activation that keeps each factor near 1, like ReLU and Xavier-sized weights. Run the deep network. The forward signal holds steady across every layer, and watch the backward sweep. The gradient arrives at layer 1 at full size. Every bar gets its share. Deep networks finally start to train. Newer activations and initializers refine this, and the very deepest need a few more tricks, but keeping the product near 1 is the foundation. Remember 3 things. 1. Watch the chain light up. Deep gradients are long products, 1 factor per layer. 2. Products drift. Below 1 they vanish, above 1 they explode. 3. The fix is balance. An activation that passes the signal through, and Xavier-sized random weights that keep it steady. So now our deep network trains, and the loss falls. But a falling loss hides a trap. Watch this curve thread every training point perfectly, and then miss the new one badly. Memorizing is not learning, and telling them apart is next. Subscribe to build deep learning from zero with me, and if vanishing gradients finally made sense, tell me in the comments. Next time on 10 Minute Science.